On a December morning in 2021, in Kourou, French Guiana, NASA program director Gregory Robinson watched an Ariane 5 rocket carry 25 years of work and $10 billion off the planet. Its destination, a point almost 4 times farther than any human has ever traveled. Astronauts repaired Hubble 5 times. If anything on Webb jammed, no rescue would ever come. Engineers had counted exactly 344 single points of failure, 1 stuck pin, 1 snagged cable, $10 billion of space junk. I am going to show you the impossible contradictions they had to solve to build this machine, and the 2 moments after it survived everything they feared, it nearly died anyway. Every one of those 344 risks came down to a few impossible contradictions, including its surprisingly tiny 68 gigabytes of onboard storage, starting with heat. To understand Webb, you have to understand what it is looking for. Hubble gave us breathtaking views of the cosmos and visible and ultraviolet light. Webb is hunting for something older. As light travels across the expanding universe from the beginning of the cosmos, it stretches. By the time the light from the very first galaxies reaches our solar system, it is stretched so far that it drops out of the visible spectrum entirely and becomes infrared. But here's the problem with infrared: it is essentially heat radiation. If you want to detect the incredibly faint thermal whisper of a galaxy billions of light years away, your telescope cannot have a pulse of its own. If Webb's own computers, sensors, or metal framework give off even a fraction of a degree of heat, it would be like trying to spot a firefly while staring into a stadium spotlight. The telescope would blind itself. So engineers had to build a shield. They parked the observatory at Lagrange Point 2, 1.5 million kilometers from Earth, almost 4 times farther than any human has ever traveled. Out there, Webb can keep its back turned to the sun, the Earth, and the moon all at once. To block that heat, it uses a sunshield the size of a tennis court made of 5 incredibly thin layers of a plastic film called Kapton. But it doesn't just block heat, it traps and ejects it. Because there is no air in space, heat can't blow away on a breeze. It has to radiate. The 5 layers of the shield are pulled tight, never touching. When the searing 230-degree Fahrenheit heat of the sun hits the first layer, most of it bounces off. The little bit that bleeds through to the second layer gets trapped in the vacuum gap and bounces sideways, radiating out into deep space. By the time you reach the 5th and final layer, the temperature has plummeted to minus 394 degrees Fahrenheit. A raging inferno on one side, the freezing dark on the other. The sun was beaten. But nothing shields Webb from what space itself would one day throw at it. Once you have a freezing, pitch-black environment, you need a mirror to catch the light, and Webb's primary mirror is a masterpiece. It is 6.5 meters across, which is massive, too massive, in fact, to fit in any rocket fairing on Earth. So engineers built it out of 18 separate hexagonal segments that could fold up like origami. But what do you make them out of? Standard glass is too heavy and warps when it freezes. The answer was beryllium. Beryllium is incredibly lightweight, rigid, and crucially, it doesn't flinch when it drops to cryogenic temperatures. Each segment started as a 550-pound block of raw beryllium. Machinists hollowed out the back of each block in a honeycomb pattern, scraping away 90% of the metal until the segment weighed just 46 pounds, while keeping its structural integrity perfect. But beryllium isn't great at reflecting infrared light. Gold is. Gold reflects up to 99% of infrared radiation. So inside a massive vacuum chamber, engineers vaporized pure gold and let it settle over the polished beryllium. They didn't need much. The gold coating is only 100 nanometers thick. That is roughly 600 atoms deep. If you scraped all the gold off the massive 25 square meter reflecting surface of the James Webb Space Telescope and rolled it into a sphere, it would be about the size of a single golf ball. That whisper-thin golden skin is the whole trick. It does one job:
bouncing ancient infrared light into the instruments, and it does not tarnish in the vacuum of space. Behind each segment sit tiny mechanical actuators that can flex the mirror by nanometers. Those segments and their actuators were built to focus light. Nobody imagined they would one day save the telescope's life. You would think a $10 billion machine capturing the most complex astrophysical data in history would have a massive data vault, but Webb relies on a solid-state drive with a usable capacity of just 68 gigabytes. Why so small? It comes down to survival. Webb is sitting 1.5 million kilometers away, completely exposed to the harsh radiation of deep space. A standard, high-capacity commercial storage drive would be shredded by cosmic rays in weeks, corrupting the data. Webb's drive is heavily radiation-hardened, designed to take a relentless beating for up to 20 years. Even with that armor, engineers expect the drive to degrade down to about 60 gigabytes over its lifespan. But 68 gigabytes is exactly enough. The telescope is highly efficient, generating about 57 gigabytes of raw science data every day. It doesn't need to hoard it. Twice a day, the telescope opens a 4-hour communication window with the Deep Space Network on Earth. It uses a specialized microwave transmitter to beam the data home at 28 megabits per second, clearing its memory banks just in time for the next round of observations. To power all of this, Webb uses a 20-foot solar array. Because the telescope flies in a wide halo orbit around its Lagrange point, it never actually passes into the shadow of the Earth. It sits in permanent 24/7 sunlight, generating a steady 2 kilowatts of power, though it only uses 1 kilowatt, keeping its thermal footprint as low as physically possible. Capturing the light is only half the battle. You also have to analyze it. One of Webb's most powerful instruments is the Near-Infrared Spectrograph, or NIRSpec. A spectrograph takes light from a distant galaxy and breaks it apart into a spectrum like a prism. This allows scientists to read the chemical fingerprints of the galaxy, figuring out what it is made of and how fast it is moving. But to get a clean reading of a faint, distant galaxy, you have to block out the blinding light of closer stars in the same frame. NASA engineers solved this by inventing the Microshutter assembly. Imagine a waffle iron, but microscopic. It is a grid of 250,000 tiny doors, each one the width of a few human hairs. Using a precise magnetic field, engineers on Earth can command individual doors to swing open or snap shut. By opening only the doors that align with their target galaxies, they can block out all the unwanted starlight. It allows Webb to analyze up to 100 different objects at the exact same time. But this brilliant invention almost doomed the instrument. In 2012, during ground testing, engineers subjected the microshutters to acoustic vibration tests, blasting them with the deafening sound pressure they would experience inside the rocket during launch. It was a near disaster. Thousands of the tiny doors rattled shut and refused to open. The acoustic stress was tearing them apart. Technicians had to halt everything, completely disassemble the instrument, and redesign the arrays before it could be cleared for flight. It was the first time Webb nearly died before it ever left the ground. After 25 years of development, Webb finally launched in December 2021. The agonizing deployment sequence, those 344 single points of failure, went flawlessly. All of them held, the sunshield unspooled, the golden mirrors locked into place. The disaster everyone feared never came. It came from the direction nobody was watching. Because space is not an empty void, it is a shooting gallery. Because Webb observes deep infrared light, it cannot be safely tucked inside a protective tube like Hubble. Its golden mirrors sit wide open to the universe. Engineers knew it would get hit by micrometeoroids, dust-sized grains of rock flying at immense speeds. They built the mirrors thick enough to absorb minor dings over a 20-year lifespan. But in May 2022, just months after arriving at its destination, the telescope took a massive hit. A micrometeoroid slammed into the mirror segment labeled C3. The kinetic energy was far beyond what pre-launch models had anticipated for a single strike. Back on Earth, alarms rang. For the second time, Webb was in mortal danger. The impact physically distorted the shape of the beryllium mirror. The segment's wavefront error measures how much it bends incoming light out of focus. That error spiked to a severe 280 nanometers. But the segmented design saved the mission. Engineers didn't panic. They sent commands to the mechanical actuators attached to the back of the C3 segment. Slowly, deliberately, they pushed and pulled the beryllium, physically bending the mirror back into shape. They couldn't erase the crater, but they ironed out the optical distortion, bringing the telescope's vision back to near perfection. Today, they fly the telescope with a new rule. They avoid pointing the mirrors directly into the rain of known orbital debris paths. When the first data came back, it sent a shockwave through the scientific community, and almost immediately, a myth caught fire online. Headlines and fringe theorists claimed that Webb had disproved the entire model of the beginning of the cosmos. They pointed to the fact that Webb was finding massive, highly structured disk galaxies existing just a few 100 million years after the dawn of time. According to the old models, galaxies that young should have been small, messy, and disorganized. But the headlines had it wrong. Webb didn't break the fundamental laws of cosmology. It did exactly what a $10 billion machine is supposed to do. It refined them. Astrophysicists realized that while the galaxies were indeed more mature than expected, some of their initial masses had been overestimated by early measurement techniques. More importantly, finding organized galaxies early in the universe doesn't mean the universe didn't have a beginning. It just means that matter clumped together, ignited, and started spinning into beautiful structured disks much faster than our previous math suggested.
Webb is doing what Hubble did before it. It is forcing us to look at our models, find the flaws, and write better equations. Webb is a testament to human stubbornness. We wanted to see the invisible, so we built a freezing golden eye, shielded it with a plastic parasol, and parked it 1,000,000 miles in the dark. The machine Gregory Robinson watched leave Earth that morning is still out there, dented, bent back into focus, staring at the dawn of time. But here's my question. With one guaranteed hour on Webb, pointed absolutely anywhere in the universe, what would you look for? Let me know down in the comments. If you enjoyed this deep dive, hit that like button. One tiny nudge, like an actuator behind a mirror segment, is enough to bend the algorithm our way. And subscribe to LynxSifts Tech and Science so you never miss a transmission. Until next time, keep looking up.